My great pleasure to welcome an old friend, David Bader, who is a leader in high-performance computing and has many, many contributions in the field of high-performance computing. But he's most well known for his work in large-scale graph analytics. And so he's currently faculty director of the Institute for Data Science at New Jersey Institute of Technology. He has previously held a leadership role at Georgia Tech, and we had some 20 years ago a very deep collaboration between University of California and Georgia Tech that David was the co-PI, and I still look back to these days with some fond memories, even though our proposal was not selected.
But it was the best proposal.
Yeah, it was the best proposal. It was only politics, and I'll explain the politics later on, is we had the wrong vendor, and actually I'm still upset at IBM crossed us on this one. Maybe, well, I shouldn't say this is on record here. I'll tell you afterwards, offline. We had the best of what I thought the best system at that time, which was an IBM Blue Gene system on the proposal, and anyway. This is old history, but as I said, I still fondly remember these days. He has been involved with many DARPA research programs in national computing initiatives. He's a fellow of IEEE, ACM, AAAS, and SIAM, and he's recipient of the Sidney Fernbach Award and a 2025 inductee in the MIMS Museum of Technology and Arts, Art, and Hall of Fame. He has authored a large number of 400 plus scientific publications and has made some real advances, especially in the early days of creating clusters in high-performance computing. And so I'm very happy to have David visiting us here for second attempt to get his visit going. And so without any more delays, welcome, David, and let's hear about your graph analytics work.
Thank you, Horst. Thank you for the nice introduction. I'm really happy to be here today, and I'm looking forward to giving this talk. This is my first trip to Abu Dhabi. I landed about 24 hours ago, got up at 5 a.m., went to the gym, may have slept last night, may not have, had a full day of meetings today. And so I'm really glad to be here tonight to give this talk. And I just appreciate everyone who come out here in person and on Zoom. What I want to talk about is some of the work that we've been doing related to large-scale data science, data analysis, and then a specialized form called graph analytics. We built an open source framework that I'm really excited by. And for that framework, we've found applications that have been enabled using our framework. And so the talk looks at a problem of trying to understand how brains work, their connectomes. And so we have some applications in neuroscience that I want to tell you about as well. So the work that I've been doing most recently has been joined with some of my current and former PhD students and research scientists, Oliver Alvarado Rodriguez, Zihui Du, Fuhuan Li, and Mohammed Dindust. Okay, thank you. So Horst already introduced me that this is just some of the positions that I've held, and I've really had the opportunity to work at the intersection of high-performance computing and applications now for many, many decades. And I've known Horst a long time. I don't want to guess how many decades it's been, but it's been a few. And the world has really changed a lot. We've gone from high-performance computing being used to solve computational science and engineering problems to now powering cloud computing, the age of AI that we're in, and all these hyperscaler data centers. So we've come a long way in computing. One thing that I really wanted to do was look at solving some grand challenges in large-scale graph analytics. Graphs are an abstraction where usually the people, places, and things become vertices or dots in the graph, and then the relationships between those objects become edges. And you've all seen friendship networks and social networks, and maybe you've seen graphs in other scenarios. But we had some challenges that we wanted to work on. For instance, we've done work in national security, computational neuroscience, where I'll do a little deeper dive in this talk, and then in scientometric analysis, which is the analysis of the literature of co-authors, references, the metadata associated with scientific papers that we publish. But all of these areas can be enabled by having a framework that lets you rapidly process massive quantities of data. And one of the challenges that we had when I started this work was that most of the analysts, most of those that need to use this type of analysis, they don't know how to program a high-performance computer. They don't know C, C++, MPI, OpenMP, CUDA. They don't know any of that. What they know is probably a little bit of Python that they picked up online, and that's it. So I have users, application specialists, that want to process up to tens of terabytes of data, massive quantities of data that requires the use of high-performance computers or supercomputers, but the users really only know some basic Python programming. And that's what's to be expected today. So we wanted to build a framework that really democratizes data science, that lets anyone anywhere be able to process massive data sets as easily as they could with Python on their Jupyter notebook on their laptop using NumPy, Pandas, NetworkX, etc., but to be able to have that run on a massive scale computer. So we built out a framework called Arcuda, which is the base. Arcuda is the Greek word for bear. And then what I'm focusing this talk on is a layer that we built on top called Arachne, the Greek word for spider. And Arachne is the graph analytics framework that I'll tell you more about today. That base, Arcuda, we've been developing for several years in partnership with the US Department of Defense and also with HPE. The software stack is all open source. We're using a compiler built under one of those DARPA programs Horst mentioned that I've been involved with about how many decades ago? 25 years ago, the DARPA High Productivity Computing Systems program had a number of vendors involved, including Cray and IBM, Sun Microsystems. This was a long, long time ago. Several of those vendors are no longer here. But the technologies that Cray built for a compiler called Chapel then found its way into HPE when HPE acquired Cray a number of years ago. And Chapel is completely open source. It's on GitHub. You can pick it up, kick the tires. It's really, really useful as a productivity layer for programming high-performance computers. I take some of my students who've never seen parallel computing before, and we're doing the hard development in Chapel, but in about a week's time, they can write performant code on a supercomputer. The Chapel server that's doing all the heavy lifting can run on a supercomputer, but it can also run on your laptop, your MacBook. It can run on an SMP, a shared memory machine, a cluster. It can run on many different target platforms. It can also make use of GPUs. So our students developing a framework just write code once in Chapel, and then Chapel can be compiled, targeted to whatever flavor of parallel computer you would like. And this has been supported by the National Science Foundation. We've been developing this framework, Arcuda and Arachne, for several years now. And the idea is that an analyst may have lots of data, tens of terabytes, as I mentioned, and maybe it's stored in tables, in data frames, and they want to do some sort of graph analytic query on it. So we can load those in efficiently into a graph format. And from that graph format, we have some graph analytics that is running on Chapel. And what the user sees, the user is sitting down here, they're interacting with a Jupyter notebook or Python, command line or in a notebook. And they're writing this code here. Just these lines are going to fire up Arcuda. They're going to load in those data frames. They're going to convert it to a graph and then run a whole bunch of graph analytics. The bottom half of that code is just running analytics to get the result. From their front end, they're going over ZMQ, zero message queue, to the back end that's doing all the heavy lifting. So they could be using a supercomputer anywhere in the world, but just on their desktop or laptop, wherever they're sitting at, they could be firing up this framework and analyzing tens of terabytes as easily as they could a small data set on their laptop. So that's the framework that we've built out. And we've been able to solve a number of grand challenge applications using the very same framework. The Arcuda layer is the data science layer, and then Arachne is the graph analytic layer. And so we're able to run problems ranging from national security to neuroscience and beyond. In national security, these are some public images, kind of an older slide that I have here to represent different types of graph analytic queries. For instance, you may have a pattern that you're looking for in some larger observed information that you've collected, and you may be looking for an exact copy of that pattern, or you may be looking for an approximate version of that pattern. So that's called subgraph isomorphism. It's thought to be in general NP hard or intractable. But if you have a large enough system and you can improve the heuristics, you may be able to run some problems feasibly that give you answers in near real time, in maybe seconds or minutes, that theoretically would be nearly impossible to compute. And in fact, these are the analytics that we're using in neuroscience. We're doing pattern matching. I'll get to that in a bit. On the right is an example of a network of the hijackers on September 11, 2001 that attacked the United States. And it was argued that if you could run an analytic called between-us centrality, you would have been able to pick out the hijackers and who was in charge of each group and so on. So this is the power that we see in national security. Again, another area in national security may be analyzing network traffic. Every time a packet moves around the internet, there is a net flow record of metadata around that packet, and that's what I have in this top table here. And in that table, there are IP addresses for the source and the destination, the port, the type of traffic in that packet, the size of the packet, many characteristics on each row of this table. And some analysts would like to ingest petabytes of this information, this net flow packet, create a graph where every packet is a edge between the source and the destination IP addresses, and then look for various patterns traffic within this set. And so here we show pulling out the vertex to vertex or edge information that we then send to Arachne, our graph processing framework, all within Arcuda. So Arcuda at a base is doing all the manipulations of data frames. Arachne is doing the graph analytics. Now, in computational neuroscience, I'll tell you a little bit more. The heart of the talk will be looking at this application in depth. We're collaborating with Harvard University, with a few researchers there, as well as the Princeton Neuroscience Institute in the area of neuroscience. We came upon this area by happenstance. I just happened to be at a meeting 2 years ago with an old friend and collaborator of mine, Hans-Peter Pfister. We were both speakers at a small little workshop at a university. And I talked about this framework and what we could do with pattern matching. And then Hans-Peter got up and talked about the computational neuroscience work that they were doing, but they didn't know how to compute the pattern matching on these large data sets. We just bolted our codes together and instantly we're able to solve some amazing problems and then continue providing solutions for the neuroscience community. This is a collaboration with Harvard folks, Jakob Treudel, Hans-Peter Pfister, and Jeff Lichtman. Jeff Lichtman is seen as the father of the connectome project. The idea is that today you can take a brain, you can slice it with very thin slices, maybe microns thick, and then you can image them at maybe 4 nanometer resolution. That creates really, really, really large data sets. Also takes a very long time to do. And this data set here that I'm showing, 1.4 petabytes of data, is for about a square millimeter of human brain tissue. There's about 50, I should say cube, 1 millimeter cube. There's about 57,000 neurons. That's then 57,000 vertices in my graph. And there's about 130 million synapses, which are the connection between neurons. And that induces about 130 million edges in my graph. So this is a very large data set. And we've been able to work on these data sets to be able to query it from the initial challenge was that either they couldn't process the data set because it was too large, and if they could, it would take weeks to get an answer. We can now do those queries in seconds. We also have, for motif finding, that's the pattern matching problem that I mentioned, we have speedups of approximately 2,000 times. And on the slide, in the lower right, you'll see a few subgraphs. This comes from neuroscientists who use Harvard's tool called MoMo to sketch out a pattern that they're looking for within the brain. Then they want to see if there are multiple instances of that in the brain. And we've been able to speed up quite substantially from NetworkX when NetworkX can solve the problem. The area of scientometrics, this is NSF-funded joint work that we have with the University of Illinois. My colleagues Tandy Warnow and George Chakow are interested in novel community detection algorithms on large graphs for the focus of the research area of scientometrics. Again, that's looking at the metadata associated with the scientific literature, with papers that are being published, the co-authors, the references, and then answering questions about the distance between authors, how well connected are they? Is an emerging research field noteworthy? Do certain authors only publish within their scopes? Many, many types of questions along those lines are asked, and looking at the research papers is the best way to analyze it. So we've been developing new community detection algorithms and working on a very large scale. And I'll save that for my next visit to Abu Dhabi and talk on some of the applications that we have here. But I want to jump now into the neuroscience area and again acknowledge the NSF support that we've had. And the framework that I built out, I promised my colleague Mike Merrill, who passed away sadly in 2022, I told him that I would always recognize him when I talk about Arcuda. This was a shared vision to build out an open source framework for doing massive scale data analytics. Mike was a colleague and collaborator for many decades. And even the night before he passed away tragically from cancer, he was on the phone with me saying, Dave, you got to do this, you got to do that, make sure you do the following. This was really his passion project. And I always will recognize him as I talk about this. What we thought was that we need productivity, and the end user is using Python, the lingua franca of data science. And so we wanted Python front end. But on the back end, we wanted high performance computing. And we chose Chapel because, first of all, 25 years ago, the US government invested in it in a DARPA program. It got developed at the time we made this decision for 20 years with some really smart computer scientists and researchers at University of Washington. And we thought, hey, this is out there. Maybe this productivity compiler for high performance computing actually has some legs to it. And we thought this would be fun to put these together and see if it could solve our problems. Lo and behold, it was a great match that we had. So jumping into the connectome project, connectome is the topology of connections of neurons in a brain. And these are some images that I have up here from a fruit fly, little fruit fly, Drosophila. It's got a very tiny brain. This is just blow up into it over here. And what you see is there's just a big mesh of neurons together. And this was really what we wanted to tackle, how to analyze these data sets. What's interesting about Drosophila is about a year ago, for the very first time, working with HHMI Genelia Farms, there's a complete labeled Drosophila brain where every neuron is identified and accurately labeled. In fact, here's an image of it. And what the neuroscience community has been able to do is now take this fruit fly and understand where the different centers in the brain are. For instance, the sensory network you'll see pop up as we come around. It's just amazing, the information and the detail here. So for instance, here's the optic network. It's located close to where the eyes are. Here's the sensory network. And you'll see these different parts of the brain or neurons connected. So there's many questions neuroscientists have. We are at the initial spot of understanding how brains actually work. This is fascinating. Imaging for this took several years, several laboratories. They, as I mentioned, have to encase the brain in resin. They have to cool it, they have to slice it, and then they image it in an electron microscope. And it takes years to image a cubic millimeter. But the technology is getting better for imaging and the desire to be able to process these types of data sets. And we're going to see these continue to grow. Now, just to show you some imagery, what does it actually look like? When we talk about a neuron connecting to another neuron through a synapse, it's probably science you all understand what it means. In fact, it's much more complicated. The axons and dendrites connect in synapses, and you can see them in this slide as being these kind of padded things. And you know it's a synapse when they touch each other. But these synapses occur on different axons and dendrites. They occur in different numbers connecting. The strength may be based on how many synapses there are between the two, and how close is the connection to the base of the neuron. There's also 3 different types of synapses based on if it's electrical, chemical, so forth, on how they communicate to each other. There's so much rich information in there. And so a fruit fly, is that going to help us with human health? Maybe not. One thing that would is understanding a human brain. But a human brain, imaging that size brain, first of all, is going to take decades, a very, very long time. We don't have the imaging capability for an object that large. And also the data set size today is overwhelming. One other challenge is that you have to decimate the brain. So unless you have someone you don't really like too much that you want to volunteer for having their brain sliced up, it's going to be hard to get a human brain for this. However, for a mouse brain, that would take about an exabyte of data. Supercomputers today can find storage for an exabyte. That's actually feasible to do. And we imagine in about the next 3 years, the technology for imaging will exist that we can image the mouse brain. And so we're going to ramp up to that because the mouse it's much closer to us as humans than is. We're going to learn so much from the exploration of a mouse brain that this is really exciting. Where I'm helping the neuroscience community is to come up with the tools that they can start to work on these larger and larger data sets. Now, going back to HL1, this is the human brain image of about a cubic millimeter of human brain tissue. And as I mentioned, it's 1.4 petabytes in this data set, about 57,000 neurons, about 133 million synapses. We've been working with this data set for quite some time. This has posed a lot of challenges. Just to tell you what we're doing with graph analytics, this is about a cubic millimeter of brain tissue, and we define motifs as recurrent connectivity patterns of neurons in the brain. So it's just like that national security image that I showed you where that pattern is located in possibly multiple places around the data set. So here, a neuroscientist may sketch out a system of neurons. And often when they're doing these sketches, it's 4, 5, 6, 7 neurons. It's not dozens, it's something they can sketch out. And they're looking for some pattern that leads to some functionality that they see in the brain, some signaling that they're looking for. And the neuroscientists will want to look for that motif, and then they'll want to look elsewhere in the brain to see, does it occur anywhere else? Is this a common motif? Are there other motifs that are very common in the brain? And so a lot of the work now is to understand these patterns or motifs. And what happens is that motif gets converted into a graph where the neuron becomes a vertex and the synapses become edges. And if you look very closely and squint, you'll see that the edges are directed because we know the signaling from one to the other. Now, this is a very simplistic way to view the brain. As I mentioned, we have some proposals that we've written to enhance our data structures. Instead of a simple graph, we now want to encode the information about where the synapses are located, on which axons and dendrites, and have much more of the geometry from the spatial aspect of the neurons and the types of connections that we see, rather than just a simple graph. So here, again, the neuroscientists will sketch out, here are 4 neurons, A, B, C, D, the types of neurons, and what they're trying to do is look for neuron morphologs within some real data set. So let me go back to that H01 human connectome data set. Doing that pattern matching, if you open up your computer science algorithms textbook, you'll find out that it's believed to be NP hard. So this is a problem that's thought to be intractable, but hey, we have supercomputers, let's see what we can do. And many algorithms have been written to try to do pattern matching. The earliest comes from Jeff Ullman, who has the original algorithm to do recursive backtracking. And the computer science name for this problem is subgraph isomorphism. So motif finding, subgraph isomorphism, and pattern matching, you can think of those as all the same algorithm. And there have been some improvements. In fact, in 2004, about 20 years ago, Cordella gave an improvement called VF2. And if you use Python and NetworkX and you call subgraph isomorphism, you're going to get VF2, an algorithm from 20 years ago. So it uses Ullman's backtracking algorithm, but it does it more efficiently. There's a refinement process. There's different heuristics. It uses much less memory and so on. So even though it's intractable in theory, in practice, if you know something about the graphs, you may be able to get some improvements. So in subgraph isomorphism, we typically have 2 graphs. One is the pattern graph and one is the full graph that we're searching for. And we are trying to solve applications broadly from different fields, bioinformatics, social network analysis, pattern recognition, and so on. So 1976 was Ullman's original algorithm, and this is exactly what you'd think of if you tried to solve the problem as a first pass. You would start with the pattern, and you would start with the graph, and you'd take maybe a vertex on the pattern and put it on a starting point in the graph, and then you just keep tracing through your pattern, seeing if in a systematic way, if the pattern matches that point in the graph. If not, you'd backtrack when you get stuck, move to another vertex, and you do that for all of the vertices until you either find a match or you find no matches after exhausting every possible search. Now that VF2 algorithm that I mentioned by Cordella, again 20 years old, has improvements on Ullman's original algorithm. I mentioned a few of these before, but what's key to note is this is the algorithm that almost everyone is using if they use a graph analytic package like NetworkX or any of the popular graph analysis tools. They all use VF2. There have been some other developments in this problem. For instance, Bonucci and Guegno in 2013 came up with a new algorithm that changes the initial vertex ordering heuristics, has different refinement processes, has more memory efficiency. So there have been some improvements. There's been other techniques to try to solve this problem. For instance, using constraint-based programming. This group in 2020, just a few years ago, have the Glasgow subgraph solver, so a completely different type of method. And also, there are some large-scale and parallel subgraph isomorphism algorithms. One, there's some focused on CPU, but for us, our data sets are larger than what we could put in a single node. There's also GPU implementations, again, mostly targeting a single node with GPUs. So these are all fantastic if your data set sits on a single node. But for us, our data set is going to be striped across a large supercomputer, and these approaches don't help us. So again, really, really great performance out of some of these up here, but our problems just need a larger system. Last year, in 2024, we come up with an algorithm that we called VF2PS, a parallel version of VF2. And there's a lot of text on the slide, but we have improvements for doing the parallelization and some new heuristics, early rejection of patterns. And this was documented in an HPEC 2024 paper. But this was really a straightforward parallelization of that VF2 algorithm. But we were able to parallelize it and do some comparisons on it. Here's the pseudocode for it. I won't go through all the pseudocode, but you'll see on the right-hand side, we have a large number of improvements over VF2 that we created as we did the parallelization. So we're able to get better efficiency, we have early termination, we have different way to order the vertices, and it runs now in parallel and faster. So this gave us a very capable code, but we weren't satisfied with it. It still was what we were able to do initially. We wanted to do better. We ran that code on Hemibrain 1.2 is a quarter of a fruit fly brain, Drosophila. And in this chart over here, we have different patterns as examples that we're looking at on the x-axis. On the y-axis is the running time in seconds on a log scale. So lower is better for each pattern. There's 3 bars. The first one on the left that's black is Arachne. The hashed one is NetworkX. And the one that's shaded on the right is motif, another algorithm for finding these patterns. And what you see is that we are running 1 to 2 orders of magnitude faster with this initial approach than you could get with NetworkX or motif. So very, very promising that we're able to improve it. But as I mentioned, we weren't satisfied. Here we're using 128 cores, and this is an old slide that I have in here. So this result is 100x to units on the log scale, but we've since been able to get 1 to 2 orders of magnitude speed up. So just looking at the slide here, it's just 100x, but we have more speed up, which is the work that we did this year that we published. So we decided to completely re-engineer how we were doing subgraph isomorphism from VF2, and this is what we call HiPerMotif. Here we have even more speed ups. So one thing that we noticed as we took patterns, here's an example pattern with 4 vertices and 0, 1, 2, 3. The pattern is the same, but how the patterns are numbered greatly affects the performance time. On the top rows, this is VF2 and NetworkX, 1,000 and 100,000 vertices. On the bottom is our last code from 2024, VF2 PS, 100,000 vertices, 120,000 vertices. And what you see in both cases here is that the running time, if you scan from left to right, based on the numbering of the vertices or the vertex ordering, there's a massive difference in running times. For instance, let me pick this top row, 50,000 vertices of VF2, 220 seconds, 6,000 seconds, greater than 16,000 seconds, we just stop the run, and 218 seconds. Orders of magnitude, or the ability to solve it or not solve it, based on just the initial ordering of just 4 vertices, well, of 50,000 vertices. So the ordering meant a lot, and the same was true with VF2 PS. Our running times are much faster, 47 seconds, 94, 142. So they're within a factor of 2 of each other here, but it's still a significant amount. Here on the next row, 120,000 vertices, there's a difference of maybe 4-fold. So we wanted to figure out what is going on. And in fact, we're able to figure out how to label the vertices to get the best performance. And it's a algorithm that I'm not going to go through in detail right here, but we find something called the most valuable edge. And we find that edge, a critical edge, by doing a walk forward in the graph, and then we go backwards in order to identify what we consider most valuable edges. And using that, we're able to get the speedups that we wanted. We could figure out what's the right ordering. So that's one of the innovations in HiPerMotif. In the paper we published, we have a number of innovations. The first is that subgraph reordering that I mentioned. Next is a step that we call validation, and that's actually reducing the search space size. The third innovation is something that we call state injection. What we found was running the algorithm step by step takes a lot of time. We found a way to time travel, if you will, in our algorithm in the search space. So we can jump forward and improve our running time dramatically. And then we have the full subgraph isomorphism. And what's really fantastic for us is that our new pseudocode here is, if you look at line 8, it's a wrapper around the old VF2 PS that we had. So everything that we're doing is outside of the last code that we had. It's just a lot of relabeling of vertices and managing these states. And this is the code that we have now that we've been using. We conducted some experiments on the HPC resource at NJIT called Wolver. It's got many different types of nodes in the machine. So here we're using our general nodes, AMD EPYCs, about 512 gigabytes of RAM per node. And this is that same HemoBrain data set that I showed you for VF2 PS, but now for HiPerMotif. We're running on 128 processors on our HPC, and we just picked a number of motifs randomly from 3 to 20 vertices, and we plot our running time is this small green bar that you can barely see. VF2 PS was the code that we had from last year, and then compared to that Glasgow, which is that constraint-based solver. And then VF3P is interesting. This is the VF2 people came out with a better algorithm that they called VF3. They parallelized it. That's VF3P that we're comparing to. So all of these are running on the same platform. All of these are parallel. All of these are running on 128 processors. And the execution time is on the y-axis. And we see speedups here up to 66x on this particular data set for patterns that we just randomly pulled out. By the way, I was at last year a meeting of connectomics in Berlin. There were about 200 neuroscientists there and 1 computer scientist, just me. And I gave an earlier version of this talk in about a 5-minute talk session. Afterwards, I had a line of neuroscientists wanting to talk to me about how do I get the code and can you work on this other problem that we have. So this is a space that's rich for computer scientists, computational scientists to get involved with. The code that I mentioned is now integrated with Harvard's tool called MoMo. In fact, we had a paper presented this month at IEEE Viz on the work that we're doing. And MoMo is a visualization engine and computational platform for neuroscientists, where it will do the transformations, and we're using Arachne to do the transformations. The user provides input. For instance, they sketch out a motif they're looking for, and we can use VF2PS or HiPerMotif to do that querying, and then the visualization comes out the other side for the neuroscientists. So most neuroscientists who are doing this connectome research are now using this platform and capability. For MoMo, this is just some screenshots from the tool from a pattern, a real pattern that a neuroscientist has sketched out. And what they want to be able to do is have results in seconds, can click through the patterns that are found in their real data set. For instance, down here, they may want to focus in on that real connectome and look and inspect the neurons in those patterns. So I had this inset in an earlier slide. Here's some real subgraphs, and our running time is often a few seconds, sometimes a little bit longer. It depends on the pattern and the data set. But NetworkX either couldn't process it or is much, much, much slower. So we're able to get up to about 2000x faster than NetworkX in most cases. Also, Arachne supports labels on vertices and labels on edges. As I mentioned, neuroscientists also may encode the type of neurons that they're looking for, the types of synapses that they're looking for, and other information can be encoded as a property graph. So subgraph isomorphism is just some of the latest work that we've done. We've actually implemented a large number of graph algorithms within Arachne, but for search, connected components, triangle counting, trust analytics, centrality analytics, and so on. So we have a rich set of algorithms, and what happens is we often work in an application domain, we have application needs, and when we have those needs, we then go to implement the routines needed to solve that application. And so the set of capabilities continues to expand, and this is all open source, so we encourage people to get a free copy of it from GitHub, install it, kick the tires on it, develop for it. The links are all in the middle of the slide here. You'll find it on GitHub. There's different packages, Chapel, Arcuda, and Arachne. So this has been a very, very fantastic project to be able to go in such a short time to create an open source framework that democratizes data science and is able to be used on real grand challenges very, very easily. The work that I've talked about here is in a number of publications. The top one that's bolded is the canonic paper that we wrote several years ago about Arachne, the graph analytic package. And then the other papers each typically correspond to one of the analytics that we created. And this work has been supported by a number of NSF awards. The top award was the main project that we had to support the framework development. The center award is the Scientometrics project. And I didn't talk about it during this talk, but I have a new project with Quan Liu at Yale on streaming or dynamic graphs and doing subgraph counting and enumeration in them. Really excited by the new work with her. And finally, my research lab. This was my research lab 1 year ago. Quite a number of people have helped with this work, including additional high school interns and undergraduates and so on. Today, my research lab with the struggles in higher education funding in the United States, this is my current lab today. So that's the impact that this has had, which slows down our progress. But I have 4 amazing PhD students. And unfortunately, a lot of those faces have disappeared either through graduation or the cuts of funding that we've seen. So I want to thank you for attending both online and in the room here. And I'd be glad to take any questions that you have. So thank you very much.
Thank you, David, for a wonderful talk and that I very much enjoyed. I have a question myself. And so the underlying algorithm is a heuristic. So does that mean if you have a very large graph and there's no subgraph isomorphism there, you search until you've exhausted the graph and it's running forever? Or do you have some approximate solutions? So that's
a great question. So we can determine that the pattern doesn't exist. In fact, in our timings, we're often enumerating all patterns, all locations where that pattern exists. So in our timings, we actually can also return that the pattern is not found. So in theory, the problem is thought to be NP hard and NP complete, which means exponential running time. In practice, we can make use of the labels, we can make use of the structure, and with the real data and a supercomputer, we can run in seconds, although in the worst case, in theory, it would take exponential time.
And the complexity is, as you said in one slide, is the number of vertices of a small graph plus number of vertices of a large graph. Is that correct?
It probably should be raised to the power.
I was wondering, I remember you said V1 plus V2.
Yeah, I think it should be raised to the power.
Okay.
That may be an old typo in my slides that I forgot to correct when I pulled this deck down.
Okay.
Yeah. So it's exponential one raised to the other because what you're doing is you're matching essentially one vertex to the other, and the combinatorics of it will give you that exponential.
Okay, thank you. George?
Thank you very much for this very nice and interesting talk. I was wondering about possible applications also for banking networks. There's an issue of resilience of bank networks to crisis. Have you looked into those problems? And can these be used in this type of setup?
So the short answer is yes. I consulted for Goldman Sachs R&D for 4.5 years. What I did inside Goldman Sachs, most of it is sensitive and I can't speak about, but I do have knowledge of the financial institutions, large investment banks, and this type of analysis can be used for numerous problems inside either a quant analysis, looking at, well, there's many areas of
systemic risk, for example.
Yeah.
Okay, thank you.
There's a question back there.
First of all, thank you so much for such a great work. I wish I had this tool back when I was doing PhD because I struggled a lot with NetworkX. And it's very exciting to see that we have a tool finally that can do such a quick computations. I have a question about the temporal structure of graphs at networks. Does Arachne can find motifs and communities for temporal networks? Because, you know, many systems that it's like static information is good, but time information is more important.
So thank you for that question. Back about 15 years ago, I developed a system called Stinger for streaming in dynamic graphs, the first of its kind to be able to run analytics on a graph that changed over time. Since then, there's been a number of developments of other frameworks and systems to do so. Today, Arachne is purely static. So you load in a data set and you process it. We were not able to build dynamicism into it because of the data structures that we're using in Chapel make it very, very hard to modify the graph once loaded. So this is a static analysis framework. That said, in the past, I built other dynamic frameworks and really was a pioneer on algorithms for dynamic graphs. And with the third NSF project with Quang Liu on my slide, we're committed to creating a new dynamic graph infrastructure, although I don't think we have the resources from NSF to do this scale of project, but we are starting work on a new dynamic graph package, taking all the lessons learned and all the capabilities that are known today and trying to create something brand new. You're welcome. And I should say most problems in the world are streaming and dynamic. I recognized that about 20 years ago, which is why I built out Stinger, because the updates either come in rapid fire. For instance, for network analysis, you have millions of updates per second, or in other problems, you have updates, batch updates daily at different rates and different sizes. But most real-world graph problems, the graph changes dynamically over time, just the rate and scale. And what you have to do in many problem domains is respond in near real time, rather than using cloud computing, MapReduce, where the analytics may take a long time to ingest the data and maybe hours to run the re-indexing and analysis. So we wanted to get that down in some of my prior projects to milliseconds. You see new edges in the graph and you want to run an analytic and have an answer within milliseconds.
Yeah, good evening, Nadine Afar. Unfortunately, I'm not a data scientist nor a computer scientist. I'm a university administrator. I just would like to know how do you find that those new advances in high performance computing, graph analytics would influence and shape future university programs, especially interdisciplinary programs, and namely at the undergraduate level? Thank you.
Thanks for your question. So I didn't quite understand what you're asking, how this will shape undergraduate programs. I mean, part of this is that before this project, it was virtually impossible to run a lot of this science. You needed to first acquire a supercomputer. You needed to program in these esoteric high-performance computing languages, and you needed a staff to run that supercomputer. There's a lot of things that you needed to do. And similar to what I've done previously in my career with Linux supercomputing, where I wanted to make supercomputing accessible to everyone, I designed the first Linux supercomputer back in 1998. That's the model for all high-performance computing today. It's a model for the AI hyperscaler systems. They're using essentially a version of that model. I wanted to do the same for data science. And what this allows is a capability that anyone, anywhere can run these analyses without having to configure a data center, have millions of dollars to buy machines, et cetera. The framework that I talked about is actually running on Google Cloud. And for the neuroscientists, anyone, an undergraduate student can be running MoMo and using all of these tools to their advantage, which they couldn't do a year ago. And so I think for education, it gives a capability that matches the scale of science that didn't exist before. So in terms of broadly impacting, there may be many other disciplines that need to do large-scale data science that just give up on problems because they can't do it. Here, they can do it. And any student can fire up Python in their favorite notebook and now be able to access this.
Yes, so there are two questions and one comment from the online audience. The first question is more of a comment. He says, thanks for the insightful talk. Could graph edit distance TED be applicable in this case? Most probably it will not scale.
So graph edit distance is really interesting. With Princeton Neuroscience Institute, we worked on a challenge where one lab at Princeton created the connectome or image a connectome for a male fruit fly, and HHMI Genelia Farms imaged a female Drosophila fruit fly. And they were looking at the graph edit distance in order to see, could you best match the male and female brains together, neuron for neuron, and identify what structures were in one brain versus the other. For instance, the female has an ovodepositor to lay eggs. Well, that is going to wire the brain differently for that functionality versus the male brain. And so we actually worked on algorithms for doing that graph edit distance type matching. I worked with some really, really, really bright high school students from Edison Academy Magnet School. Princeton had a challenge, and we were one of the top groups competing against PhD researchers at labs who were working full-time on this. My high school students would skip a class here or there and worked with us to do extremely well. In fact, we have some of the top results. There's a contest that's still running, and we have some of the best matchings of any group with the algorithms that we had. So I think graph edit distance is really, really useful, and among a number of other algorithms that could be also employed.
Thank you. And then the next one is from an ethical standpoint and speaking one data scientist to the other. When sharing results from Arachne and Akuda, how does Prometheus share his flame without burning the forests?
So in terms of ethics, that covers all of computer science. And the security around data sets, the ethics, are a very, very important topic, but somewhat outside of the scope here. So in the use cases that I've showed here, we're using open data sets or publicly accessible data sets. And this could be used in other environments. It could be used on premises in other environments with private data sets. But I think the questions about ethics and which leads to the sensitivity and security around the data sets really matters no matter what type of computer science we do.
Yeah, and there's a follow-up question. Are there any known biases within Arachne's techniques? The different isomorphism techniques sound fantastic, but I'm a stickler for the wisdom of when to read between the lines and when to take things at face value. Survivorship bias, correlation versus causation, etc.
So very interesting question about bias in the algorithms. In fact, the running time is biased by how the graph is presented to us. And that's where we use vertex reordering. But the solutions are not biased. For instance, when a neuroscientist looks for a particular pattern, we can give them a list of every location of where that pattern exists. Right now, we just have an arbitrary order. Maybe there's bias in the sorting of that list or how that list is ordered, but we're not picking out a particular single instance. We could, and that would have some bias from the algorithm, but that's not an area that we've really studied. Unlike in AI, which this is not artificial intelligence. One of the goals of this project, I should say, is to understand how a brain works. Our brains use, some watts of energy. They're fueled by water and some of the snacks outside, and they are doing more work than some of the LLMs that are using megawatts of power. So if we could understand how the brain actually works, maybe we could improve the deep learning models and do training without big data centers and LLMs. And so part of this is to actually understand real intelligence and real brains in order to improve the artificial ones.
Thank you, Professor Bader. I'm a climate scientist, so I was wondering if you've done any relevant applications in that realm, specifically in terms of causality research. So as you know, we struggle as well with petabytes of data. It's a similar problem in neuroscience. And you mentioned MoMo is running on Google Cloud. So I was wondering if it's also on the back end of Google's Earth Engine, for example, one of the applications they have for climate science.
Thank you. On the last question, I'm not sure. I would have to look into that. And on the first part of the question, graph analytics are used in climate science. In fact, now it's many, many years ago, I had a collaboration with Pacific Northwest National Lab and the German Meteorology Society, from memory, DRKZ, something close to that. It's been, yes. And that, is that Tom? I'm drawing a blank. It's been too many years, but we had meetings and we're actually working with the German meteorology research center on applying graph analytics for global weather, where rather than looking at the physical properties of a grid around the Earth, we're looking for higher level objects like storms and other things and connecting them together, sea surface temperature, a variety of things that can be modeled in a graph versus in the pure physical domain, spatial temporal physical domain. So yes, but I haven't worked in that area, that application for more years, probably 20 years.
Thank you very much for the session and a long flight that's yet still, you're still active here. I was wondering of the applications in the healthcare space. The user's biology is not linear. We have networks, interactions, causality, multi-node signals between sleep, medical labs, wearable data. So much information out there that can be finally put together and to empower people, users, patients to connect all that information and make some sense of it and derive strategic insights. I was just wondering to what extent you've explored anything in the healthcare space?
Well, we actually have done quite a bit, and it's not in this slide deck, so I was thinking I'd go to a backup slide. It's just not in the deck that I have here. But for instance, there's a couple of uses in health sciences. First is many healthcare records are large repositories, and you may want to view it in terms of family connections or ways that there are relationships between the patients, maybe by location, address, things like that. So we've looked at extracting records from electronic health records and then creating a graph out of the people and places within those records to do deeper analysis. Also in the health space, contact tracing that we all know about from COVID is a great example of how to use graph analytics. And there are other use cases that we've looked at, because in those records, often there's connections that today the databases may not connect with each other, and that we have information coming from multiple silos of data. The graph allows you to merge those data sets together, and to do so that you can find the connections that would be impossible to find in the siloed data.
That's right, because the system is so incredibly fragmented. And the idea was that how do we finally combine all this data and derive real root cause problem solving as opposed to symptoms just on the basis of such fragmented, broken data?
Correct. Early on, we worked with Mayo Clinic in the US, and they have a special projects group that we worked with on looking at graph analytics within the medical area. They were very advanced. In fact, at Mayo Clinic, they had decades of patient records and multiple generations of families. And we looked at graph analytics on those patients and records. Mayo Clinic is very innovative in a number of areas. They've been able to discover things that would never have been discovered without graph analytics. So
can it look at continuous data like from wearables as well, or just static one-time snapshots like medical labs? Or
I mean, the continuous data, it's really discrete. It's not actually continuous. The time steps are just small.
Right.
And what we get from wearables is much less than, say, a cybersecurity application. In fact, I wanted to look at health, and I decided many years ago to get a Fitbit so I could use my own data and not worry about HIPAA. I could just release my data publicly if I wanted. Which I've done before. And so I was thinking exactly about that. And it's a very interesting area.
Appreciate it. Thank you.
You're welcome.
David Bader, one more time for his excellent talk and for his long trip to Abu Dhabi. And of course, I'd like to invite you to join us for refreshments and ask more questions afterwards.
Thank you so much.